Hi everyone. Today we are going to talk about tensor-parallel. So just a quick reminder, last time we talked about modeling, the process group manager, which was the central part of the video, and the data loader. So just a reminder of what is the process group manager. So this is a way to go from a set of raw GPUs IDs and to create a subset of GPU's ideas that make sense in the parallelism schema that you have used in tensor parallel, data parallel, or pipeline parallel. This way, in tensor parallel, you only want a subset of GPUs to communicate together, and in PP, in pipeline parallel, another subset of GPUs to communicate together. So to understand tensor parallel, before we have to understand at which level it operates. So by that we mean that we are going to split linear layers, because in deep learning it's a stack of linear layers. And what is linear layers? It's actually you have your input x and you have a linear, and what you are actually doing as an operation is x times matrix multiply with a w that you usually transpose to match the dimension, otherwise you cannot do the matmult, and then you add a bias. Most of the time in tensor parallel, the bias is not used because it's too small to tensor parallel. It makes not much sense because it's just like a 1D vector. And then, just for the simplicity of our example, we are going to omit the transpose, but usually there is a transpose. So, for example, on a single GPU, you have this, okay? And to get the 20 here, you can just simple matmult, 0 times 10 plus 1 times 20, you get 20. But there is a time where your weight doesn't fit into a single GPU, and this way you have to split it into several GPUs. And if you want to split into several GPUs, your weight, well, as you have seen, there's two dimensions on your weights, either column or rows. So there's two ways to split your weights. Let's see the first one, for example, splitting column-wise, okay? So I'm going to copy paste the picture that I've made before the video. So you see here, we have the weights that are splitted in column. You have 10 here, 10 here, 20 and 20 here, okay? And same for second GPUs, 30, 40. So just since the dimension match with the input for 2 and 2, 1, you can do the matmut, because if it was like 1, it's not possible. So the input is the same. We broadcast the input in each rank. We do the matmult in each rank and get these matrices. And here, to get the real result, like this one here, since we have shards, we have to all gather. All gather is just a way to concatenate some matrices together between ranks. So here you see this one is here and this one is here. Okay. So for column linear, actually do is just broadcast the input et outgather the output. Now, what about we split row-wise? Okay, this way. So we can just take this schema here. Okay. Up. We just make it bigger. And maybe up. Reduce this one just for now. Okay. So what do we do here? So we see that we split row-wise, 10, 30, then 20 and 20, 40. But here the dimension of the weight is 1, 2, and the input is 4, 2. So what we have to do is to split our input as well, so that we can do the matmult. Because here it's 1 and 1, the dimensions are matching, so you can do matmult. So we do the matmult in each rank, okay? You end up with these two matrices. Now what you have to do to get the full matrices is not gather, because you already have the final shape. You have to all reduce. And all reduce, what it is doing element-wise addition within the same column. For example, here, the 0 here, and the sum with the 20 gives you 20 here. If I go to 20 here, plus 60, it's 80. If I do 0 plus 40 here, I get 40. And if I do 60 and 100, I get 180. Okay, so for raw linear, what we have to do is simply a scatter of the input and then a null reduce of the input. So now you tell me, but yes, in deep learning, there is not only one linear, there is like several linear, okay? Which means that we may have to do combination of column and row, for example. In deep learning, usually you have like first linear, and then you have activation function like a GLU, okay? Then you have a second linear, okay? A second. And the reason you use an activation function is to bring non-linearity to your model. Otherwise, they will learn nothing. It will be too easy or overfitting. So you bring this non-linearity between layers. So since you have like two layers, you may have two combination of splitting the weights. So you may have column plus column plus row plus col, or row plus row. Okay. But the thing is, which one to use, actually? I cannot like do randomly one of the four, and no one will be there will not be any standard way of doing the splitting. It's a mess. But let's think about the thing a bit. Like you have the GLU here. The GLU has an issue. Depending on which way you are splitting your weights for the first linear. So suppose we split the first linear, okay, and we do the column way. So we if we look at this thing, we do x times w0. We have to apply the GLU here, okay, to the first rank, and then we do the same thing for the second rank, okay, and at the end we have to altogether, okay. So altogether is essentially just concatenating. Okay. Well, basically this is the same thing as doing the GLU of the cat of each output of xw0 and xw1. If you don't trust me, we can verify this in code. So I have this small function, script, where you take an input, you have a weight, you shard the weight, you do exactly the operation I do during the notebook, the cat of the GLU or the GLU of the cat, and then you press an assert, and you see that it will match. Taking a bit of time just to run the script. Okay, column linear match. Nice. Okay, now what if we start the first linear splitting with a row? So if we look at the thing, we have xw0, xw1, but we have to put the GLU on it, up, GLU, up, and then since we do our reduce, we have to sum, okay? Well, it's different in terms of result than doing the GLU of xw0 plus xw1. And we can verify that with the code. So this small code below, if I just comment this, x is splitted, w is splitted. Remember in a row we have to split the x, otherwise we cannot do the mat mult with the weights because the last dimension of x and the first dimension of w is not matching. So you do the GLU of the sum, and here the sum of the GLU, sorry, and then the GLU of the sum, assert, and let's check if it match or not. Yeah, it's not matching. Every values are different. So that means that we are we can remove every schema that starts the splitting of the first linear with row. So we are left only with two options. Okay. So which one to choose? Well, just let's try them both and see if we can see some redundance or something. So we see that the first linear is doing a broadcast, then you have all gather, and then we have to broadcast again because the column linear is doing a broadcast, and we finish with the all gather. So you see that here we have a total of 4 communication. Okay, broadcast, all gather, broadcast, all gather. What if we do colon plus row now? You see here that you have broadcast. This is one communication. Here we don't do any communication because why? Row linear needs the input to be splitted so that we can do the multiplication with the weights, okay? And since here, at the end of the column, we have to do all gather, but we don't need to because we can reuse this output for the row linear because it's already splitted. So we don't need to do all gather. So it's cool. And then at the end, for row linear, at the end, we have to do the all reduce, which means that here we have two communication. So here we can see a clear winner. We see that with the column and row linear schema, we are actually saving two communication. So it's more efficient to do column plus row. Okay, so it's good. So now we understand the theory. We can go to the code and see a bit about the implementation details. So what are the new changes in the step 4? Everything was view. I will just undo that. Up. Okay, so we see some changes in the call to flash attention, just some asserts, not really important. But the main part is this whole new file called tensor-parallel. So you have like TP communication, you have the end of it, a function called apply tensor-parallel, a class column parallel, row parallel, vocab parallel. We didn't talk about it yet, but we will. And that's it. We can view. And after that, we have the train. You see that the API changed a bit. We apply this function tensor-parallel to parallelize our model. So let's take a look a bit on what is this apply tensor-parallel, because now it's cool that we can we know how to parallelize the linear, but what about the transformer now? So there is this replace module function. So basically what we are doing is monkey patching. We have existing PyTorch linear and we replace the linear layer by a linear that we have created. In our case, column or row or vocab. Here, there's a list of decoder layer, attention QProj, attention KProj, VProj, outproj, the MLP up, gate, and down. So, if you remember the architecture of transformer, the QKV are done in parallel. And then, the output of the attention is then used in outproj, okay? So what we can do actually is those three, we can apply column parallel, and the output that they use, that they produce, can be reused for outproj, and this one can be a row linear. Okay, this way we still have this two coms save up. So indeed, we do kproj column, vproj column, outproj row. Same for MLP. MLP it's the same thing, that in a sense that the up and the gates are done separately because there will be element-wise multiply, and then this will be used for the down proj, the down projection. So you see that here we do column form MLP proj and get proj, and the down proj is row. Okay. See here we are replacing the module of the embedding. We'll talk about this later. Then we have the final proj. So here this one is the column because we start always the new linear with a column. But you see that here the gather output is equal to true, because since we don't have any more layers after that, we don't need the split output. We actually want the full output. So that's why we have to trigger the gather output. I mean, we have to trigger the gather call so that we retrieve the full output, sorry. So let's check about how we actually, implement the column parallel linear. So in the init method of column parallel linear, what you want to do is to create the sharded weights. So how do you do that? First, you have your out features. So that's why I say that tensor parallel is applied on the hidden size dimension, because this is what you are actually cutting into 2 if you have 2 GPUs, or into TP word size in general. So once you have like the output size per partition, you have to create a weight, a parameter weight with this shape. Notice that since we are doing column parallel linear, we have to put this variable in the first dimension, because with the PyTorch API, when you do functional linear, the matmult, it will apply the transpose on the weight. So this way, this one will go during the computation as the last dimension. So we are doing column parallel, but the weights needs to be initialized in the first dimension so that it gets swap transpose during the matmult in the last dimension. So how do we initialize the parameter, the weight? So if it's TP, if there is no TP, you can just follow what the PyTorch documentation says about the initialization of the weight. But if you have more than you have TP on, you have to do a master weight, initialize with empty, then initialize with the uniform what PyTorch says, and after that you have to create a list of weight, split it. You have to split this weight, and when you have split this weight, you have to assign the correct weight chunk to the current weight variable of your current rank. Okay. So row parallel is the same ID, except that this time the dimension is on the last, so that the transpose go on the first dimension. And the reset parameter is the same. Just make sure to use the split on the right dimension. Okay. So now let's talk about the forward pass of column parallel linear. So remember, we are actually doing in the column parallel a broadcast, okay? And then an all gather. So you see indeed that here there's a function called copy, then you do to get the input parallel, and then we have the f linear, and then we have the gather, okay? So if we look at the copy function a bit, it's see that the forward is just returning the input, so it's basically a broadcast in a way. And after that, after the copy, you do a matmult. And once you have the matmult, you have two choices. Either you gather or you are not gathering. But since we are doing the column plus row successively in column linear, that's why we put the argument gather output equal false for column linear, except if we specify manually the gather to true. So we are not going to gather. We will leave the output splitted. And then once you have the output splitted, that will get fed to the row parallel forward. So this is the row parallel forward, okay? Row parallel, the forward is here. Well, you see that we can do automatically, we can directly do the matmult. So we are actually at this stage. Sorry. We're actually up at the stage here, where we do the f linear. And then at the end, we have to do the reduce. The reduce, all reduce. And yeah, we can take a look at the all reduce, which is in the forward. This all reduce sum, and we have to make sure it's within the TP group. That's why we create this process group manager. We want to all reduce only with the subset of GPU that has the shards. Okay. So now we can move on the backward. So to understand the backward, here, since we do broadcast and all reduce, the backward is the reverse of the forward, which means that here we have to do the broadcast, and that here we have to do the all reduce. So if you look at the backward pass of the reduce, this is indeed the copy, grad output. And if I check the column parallel, the backward of the copy, you see that it's indeed the backward is indeed a null reduce. So that's how you make your distributed communications differentiable is by overwriting the forward and backward of the autograd function. That's how you do it. Now we can focus a bit on this part, on the final layer when the gather output boolean is true. So the final proj has to gather, okay? And so we apply the gather. We can maybe check the content of the gather. So you see here that it's a forward. We do some stuff. This is actually not correct. Contiguous? No, you have, it's correct. You have to make your input contiguous to use all gather. After this link to the PyTorch code. You hold the all gather and you cat. Okay. Then you have the backward. Okay, the backward. Since in colon parallel, if you remember, broadcast all gather, which means that in since you all gather, okay, the two shards, when you compute the gradient, you have to distribute the gradient of this shard to this, okay, and this one to this. That's why the backward pass of the gather is you split your gradient you split the gradient to the specific rank. So we do chunks of TP rank. Okay. So now we can talk about the vocab embedding. So vocab embedding, we have to understand what is the vocabulary embedding in the first place. So I see it as a lookup table. For example, let's say you have the embedding weights, okay, which are, for example, 10, 20, 30, 40, 50, 1, 2, 3, 4, 5, 60. Okay, let's say it's of size 6, vocab size equals 6. Okay, and you have this input, okay, that is 1, 4, I don't know, 2, 5, okay. So when you do f embedding of x ew, what you are actually doing is you're taking the index, the content. This is index, and you index the w to get the context. So here, 1 is in here, so 20. 4 is at this position, and you get 50. 2 is at the position 30, is here, and the content is 30. And then 5 is here, and the content is 60. Okay, so that's basically what the embedding is doing. But what if we have two GPUs now? So the logic is as following. You have two GPUs, okay? Rank 0 and rank 1. And what you will do is shard this thing into two. Okay, like this. So which means that you will have EW0 with only a chunk of the embedding, and you have this, which is 40, 50, and 60. Okay. And then now you have to make sure that the range of your embedding is different. Here it's going from 0 to 2. And here it's starting from 3, okay, the 3 here, to 5. Okay. Okay, all good. So now your input is still the same, huh? 1, 4, 2, 5. So x equal 1, 4, 2, 5. So the first thing you have to do is create a mask of your input. So you have a mask saying that does 1 belong to the range of your range of index? So true. Does 4 belongs to 0 to 2? False. Does 2 belongs to the range? Yes, true. And does 5 belongs to 0 to 2? False. Okay. So now after that, what you have to do is mask the input. So x of mask. Okay. And you get something like 1, 0, 2, and 5. Okay. Once you have done that, well, you can actually compute the embedding with the masked x. and EW0. So you get actually equal to a list with 1, which is equal to 20. Then the 0 is equal to 10. The 2 is the 30. And the 5, which is supposed to be 0 here because it's false. So, sorry, typo. 0, which is 10, because index 0 is 10. So you see here, there's an issue because you have like 10, 10, which is not what you wanted, because it's supposed to say that it's not in the range. So you have to mask again this output. Mask with the same mask that you have built, and then you get 20, 10, no, 20, 0, 30, 0. Okay. So now let's do the same thing here. You have the same input, 1, 4, 2, 5. I just put it in red actually, in green actually, okay? Just to make it clear. Or maybe not this color. Okay, and this as well. I will write in the right. Okay. Okay. Say it's on the second GPU. So you have the mask. Do the same thing here. Does one belongs to 3 to 5? No. False, true, false, and true. You apply the mask. You get 0, 4, 2, 0, and 5. Then you do the F embedding after X mask, EW1, and you get here 0, it's 20. So no, before that there's an issue. The issue is here. You have 0 for 5, but the 4, if you are going to do the index X max in the embedding weight, you see that here it's ranging from 0, 1, 2 here. So, and if you do 4, you have out of index array. So what you have to do is shift by the vocab start here, 3, so -3, to be within the range of your embedding. So 1, 0, and 2. Okay, so actually here we didn't do the shift because actually the beginning is 0. So -0 gives you the same thing. Okay, so it's no changes. Okay, so now we have Xmax AW1 that is shifted. So 0 is here 40. 1, 0, 1 is 50. 0 is 40. And 60 is 2. 0, 1, 2, 60. Okay. So now we see we have the same problem. So we have to mask again as in the rank 0. So we apply the mask which is here. False 0. True 50. False 0. True 60. Okay. So now we have the output in both embedding. Well, what we have to do to retrieve the full embedding? Plus. So this is an or reduce. And we get 20, okay? Then we have 50, then we have 30, then we have 60. And is this the same as the here? Well, yeah, 20, 20, 50, 50, 30, 30, and 60 here, and here. Okay, so we have the full pipeline then. Let's check if in the code it is reflected. So here this function, self vocab start index, vocab and index. So this is basically for each rank to find the range that are here, okay? Those two. Once you have done that, you have to first do the masking thing, like creating the mask out of your input. And once you have done that, you can compute the embedding. So you see here, we create the mask, then we have to shift the input so that it stay within the range. Otherwise, when you do you compute the embedding, it will go out of range. And we compute the embedding, and after that, you have to make sure to zero out your output, as we did here. And after that, you have to finish with all reduce to get the final output. So that's it with the vocab parallel. Let's run the code and compare with the baseline. So last time I didn't run log in 1dB the training step. I was just want to here run and check in 1dB the loss, and normally the loss should be pretty much the same without any parallelism and tensor parallel. Actually, it's a bit different because when you do tensor parallel and you do matmult on smaller matrices, it will trigger some different CUDA kernel, and usually you since floating point arithmetic is not like, if you do a plus b is different from b plus a, it's not exactly the same, but the loss should be almost the same, but you can spot some difference. It's okay. So now I'm running the data loader, the previous runs, the previous step 3, just some run to log into 1dB here. So let's see. Okay. So it's logging. We have the loss. It's going down. Nice. Okay. Now we can go to step 4. Up. And in step 4, I can train and see. I'm running this command where I use TP4, TP size 4, and then the same settings with max token and stuff. And I run this, and we wait for 1dB to check for correctness. Of course, what you have to do is running on more tokens and stuff, but just for the sake of the tutorial, we can just do on a smaller scale and less data. So it's called TP naive. So let's see if it's created in 1dB. Okay, so it's starting to be created. Taking a bit of time to start. It's going, the loss is going down. It's pretty much the same. Now we can check the log. I'll refresh a bit. Oh, I don't have enough battery. 12%, it's okay. Okay, so you see, so the loss is it's quite matching. Huh? Maybe we need more step, of course, but it's pretty much similar. So that's a small gap. And in general, with larger data sets, larger model, the gap is very small. Actually, if I look at Picotron tutorial, I run on the several config here, and see that from these images, at the very end, after all the implementation, TP4 baseline, TP4, and the 3 of them activate, you see that the loss at the very beginning is a bit different, but at the very end is matching. Okay, so thank you very much for watching this video, and see you on the next one with data parallel, this one. Bye.